So, in this lecture we shall be looking at two examples for device interfacing. Deliberately we will take some examples which are simple enough, so that you can actually understand what is happening inside, and some of the IO transfer techniques that we have discussed earlier, you can see how we can use them here. Okay. So, the title of the lecture is some example device interfacing. So, as I said that we will take two simple examples. So, one is the problem of interfacing a keyboard, and the second one is the problem of interfacing a printer. Let us look into this one by one. Keyboard interfacing. Well, all of us use keyboards in our computer systems, in our mobile phones, wherever we have a mechanism for entering something. So, means even in our microwave oven we have a version of the keyboard, even with our TV remote there is a keyboard, with our air conditioning machine remote control there is a keyboard. So, any device which allows user to apply or give some input via pressing of switches is a kind of keyboard. Okay. So, a keyboard in a generic sense is nothing but a set of push button switches which are called keys, which are interfaced to some system. Well, computer may not be the only thing, it can be an embedded system also, microcontroller small. So, this is an example of a small keyboard where you can see that there are 16 such keys, and this is a standard computer keyboard which is also conceptually very same. Now, here this small example, as it shows that the 16 keys we have organized in 4 rows and 4 columns. Now, logically speaking, we arrange the keys in this fashion only. Why? See, there are rows and columns, we connect a key at the junction of the rows and columns, like you see it is something like this. Suppose I have some row lines and also there are some column lines, but they are not connecting, they are on a different layer, there are column lines. Now, what do? We connect a switch between every row and column. There is one switch connected here, there is one switch connected here, one switch connected here, like this. So, in every junction there will be a switch. So, for a 4 by 4 thing there will be 16 such switches. Okay. So, whenever you press a switch, the corresponding row and column will be connected. This is electrical property of the keyboard. Now, the computer keyboard that you see, well, it may look like a little longer one, a longish thing, but inside if you see the layout, the keys are again laid out logically in a matrix form. Because there is an advantage of laying out in a matrix form, as we will see later, the number of interconnection lines get reduced. Okay. So, if you have a 2-dimensional matrix realization, the number of lines required will get reduced. This we will see a little later how. Okay. Let us come into the problem of interfacing of switches. Let us start with the simplest scenario where we do not have matrix kind of a layout. We have a set of 8 switches. Let us see how we have connected them. There are 8 switches which are shown here. So, one end of the switches, it is connected to ground, and the other end is connected to the lines of an input port. This is an input port of the computer, and this switch can be regarded as an input device. So, whenever you are pressing a switch, the state of the switch will be coming as an input data. Now, you see here whenever you press a switch, because it is connected to ground, that line will definitely become 0, it will be connected to ground. But if you do not press it, it is open, then this line will be floating. So, you really do not know what voltage will be coming here. So, to be sure that you are having some voltage here, you connect some resistances on all the lines. These are called pull up resistances, and they are connected to a positive voltage, which can indicate logic 1. So, now what will happen if the key is not pressed, then this VCC will come and appear here, this will be treated as a 1. So, if I have not pressed any keys and if I read this input port, all these lines will be 1, 1, 1, 1, 1, 1, 1, 1, 1. But if any of the key is pressed, the corresponding input will become 0, right. So, here let us see how we can check the status for asynchronous transfer, because you recall for asynchronous data transfer or handshaking, we mentioned that the CPU will be continuously checking the status of the device. Are you ready? Are you ready? If it is not, it will go back and check again. So, when the device is ready, then only it will come out and read the actual data. So, here checking for the status is very easy. You see, if the device, if you have not pressed any key, which means there is no input. So, if you read from the port, you will get FF all 1, 1, 1, 1, 1, 1, 1, 1, 1. So, in hexadecimal it will be FF. So, if it is FF, you mean that no key has been pressed, there is no input, you go back and continue checking. But as soon as you see that it is not FF, which means one of the switches is 0, then you come out. Then first thing you will have to check which of the bits is 0, that you can easily check. There are shift instructions, there are bitwise AND OR operations, you can check the bits, which bit is 0. If the bit number 0 is 0, then you do something, if bit number 1 is 0, you do something else, depending on what those switches indicate, right. So, if you connect switches like this, it is very simple, but there is one problem. Here you see we have 8 switches. So, one 8-bit port you can connect them directly. Now, I tell you that well I have 100 switches. So, where do you connect them? You will be needing 100 lines of ports, large number of ports, not only that 100 connections. So, the wires also there will be 100 wires. So, as the number of switches increases, the complexity of connections and the number of ports will also increase. This is one drawback. Okay. So, now let us, this is the same thing. So, here what I am saying is that just now I say that for n number of keys, if there are n number of keys, number of port lines required will be n. I need n number of lines. So, if there are 8 number of bits per port, then I will be needing n divided by 8 ceiling of that many ports, okay. And I will be needing one line for every switch, there will be n number of lines also. This is too expensive to use and to lay out, okay. That is why people do not use, although this is very simple, the way you check whether a key is pressed or not is very easy, but because of the complexity of wiring, people do not use this. So, what we use? We use a matrix keyboard, just the kind of keyboard I just now mentioned. Here I have shown an example of a 4 by 4 matrix. You see, there are 4 row lines, there are 4 column lines, okay. These are small switches connected between a row and a column, right. So, you see, once you connect these 16 switches in a 4 by 4 matrix, you do not require 16 wires, you need 4 wires in the rows and 4 wires in the columns, right. And as you can see that there are resistances to a positive voltage, the pull up resistors, connected to the rows as well as columns. Let us see how it works. The first thing is that number of wires are getting reduced. So, for n number of keys, if you can lay them out in a perfect square, if n is a square, let us say 64 keys, then you can lay out as an 8 by 8. So, we will be needing 8 wires on this side and 8 wires on this side. So, twice square root of n. So, since we have this nice property, so even for a 64 keys you need only 8 and 8, 16 port lines, not more than that. Okay. This is one good thing. Now, let us see how we can check whether the device is ready to transfer data, that means some key is pressed or not. How we can check that? How to detect the status of the device? Well, there is a simple way. You output all zeros to the rows, then read the column port and check whether all the bits are 1. If any of the bits is 0, it means a key has been pressed. Look at this diagram again. You output 0 0 0 0 on this port line. So, these lines are 0 0 0 0. Now, suppose the keys are not pressed, none of the keys pressed. So, the column lines, they will all be connected to the plus voltage. So, they will get 1 1 1 1. Now, suppose this key A is pressed, I have pressed this key. So, this row and this column will get connected. So, this was 0, this 0 will propagate and this bit will be 0. So, if I read and if I see that this is not 1 1 1 1, which means at least one of the key has been pressed. So, for asynchronous transfer, the way we check, suppose we have to check the same thing. So, how do we do it? For asynchronous transfer, we have to check whether a key is pressed or not. So, this you can do like this. So, I am showing the flow chart of the code. Output zeros to the rows. Read column port, then you check here whatever you are reading, are they all ones? If you see it is all ones, which means none of the key is pressed. So, in that case you have to go back and check again, and if any of the bit is 0, some key is pressed, you can go ahead with the next step. So, this is how you can check the status of the device to check whether the device is ready to transfer data or not. Okay. This simply output 0 and read the column, this method. Okay. The next question is how to determine exactly which key has been pressed. Now, for this purpose we need to do something or carry out something which is called keyboard scanning. Here one of the rows is made 0 at a time and the column bit is checked. Like I will illustrate with an example. Let us see. Suppose I have 4 rows and 4 columns as that example shows. There are 4 rows and there are 4 columns. So, there is one port connected on this side, one port connected on this side, and there are pull up resistances, those are there, those I am not showing. Okay. These are all there. They are all connected to the positive supply voltage. Fine. Now, I want to check whether a particular key is pressed or not. Well, I can identify some row numbers and column. Let us say, let us follow convention. This is my row number 0, row 1, row 2 and row 3, and this is my column 0, column 1, column 2 and column 3. Now, here what I do is as follows. Well, I keep two counters. One counter I call it as the row counter. This is just a variable or a register, and another which is called the column. Okay. So, initially I set the row counter to 0, and here when I set the row counter to 0, what I do, I activate row 0. Activate row 0 means I output a 0 on this row, but all others are 1, right. I activate row 0. Then I read the columns and see that whether any of the bit is 0. If I see any of the bit is 0, it will mean that one of the keys which are connected to the row number 0 must have been pressed. Because of that, this 0 is coming here. But if I see it is all 1 1 1 1, which means row 0 no key has been pressed, then what we do? Then we increment row to 1 and activate the next row. So, now we make this as 0 and make the others as 1. So, now you do the same thing, you check whether the columns any of the ones are 0 or not. So, in this way, suppose I had pressed this key was pressed. So, in row 1 it will get detected. So, I am reading something which will be 1 1 0 1. I get this data because this will be shorted, 0 will be coming here. This is not all ones. Okay. So, now I can identify one thing, that row number I have identified, there has been a key pressed in row number 1. Now, in whatever I have received, I will check the bits, which bit is 0. I check bit number 0, 1 and 2, bit number 2 is 0. So, I set column number to 2. So, I have got row number and column number. So, I can define a key code like this, row number multiplied by 4 plus column number. This is typically done in a 4 by 4 keyboard. Like if you do this, so how the keys will be mapped? Row number is 0, 0 multiplied by 4 plus column. So, 0 plus 0, this will be 0, 1, 2, 3, then row 1, 1 into 4 plus column, 4 plus. So, this will be 4, 5, 6, 7, 8, 9, 10, in hexadecimal it is A, then 11 it is B, 12, 13, 14 and 15. So, you see, using this kind of keyboard scanning method, we can identify both the rows and columns, and once you have identified both the rows and columns, then we can identify which key has been pressed. But before you start this process, you have to do this. You have to first check whether a key has been pressed or not. If the key has been pressed, then you move on to the keyboard scanning, right. This is actually how the thing works. Okay. So, now you think that you can make some small changes by and make the keyboard interface work in an interrupt driven mode also. See, in the earlier case what we saw is that just for checking whether you are pressing any key or not, you are outputting all zeros and you are checking whether the column is all 1 or not. Now, here what we are saying, we will do something a little different. So, I am again drawing the diagram, but I am not showing the switches and the resistances, just the rows and columns I am showing. 4 rows and 4 columns. So, what I am saying is that we will be connecting 4 AND gates, and the output of the AND gates will be driving the rows, and you have the port will be driving one of the inputs of the AND gate. But while the other input of the AND gate, they will be made common. This you can call some kind of control. This will also be controlled by the CPU. This will be connected to some other output port. Okay. So, this is one change you do, and the another change I am suggesting is that you use a NAND gate and connect the columns to the NAND, and the output of this NAND you connect to the interrupt input of the processor. Just think what happens here. Here you recall these are all pulled up to positive voltage. Okay. These are all positive voltage, and when you are checking whether the key is pressed or not, so under normal conditions control will be set to 0. Normally control is 0, right. Control 0 means what? So, one of the input of the AND gate will be 0. So, these lines will always be 0 0 0 0. Now, suppose any of the key is pressed. Well, suppose it is not pressed. If it is not pressed, then all these lines will be 1 1 1 1. The output of the NAND will be 0. So, there is no interrupt. But if any key is pressed, because you are applying all 0 by default, that particular bit will become 0, and correspondingly the output of the NAND gate will become 1, and an interrupt will be generated. So, the processor will know that well there is an interrupt, some key has been pressed. Now, it will jump to the ISR, and inside the ISR that keyboard scanning routine will be there. So, when you are inside the ISR, when you are doing keyboard scanning, of course, you will have to change the control to 1 during that time, because now whatever you are sending over the port, that should come to the rows, right. So, with this hardware modification you can have means interrupt driven keyboard interface also. So, whatever I have illustrated is written here exactly the same thing. The rows and keyboard connected together, columns are connected, NAND gate, output of the NAND gate will be become 1 whenever a key is pressed, and inside the ISR, as I said, the control inputs of the gates are set to 1, and normal keyboard scanning is carried out to identify the key pressed. Now, let us very briefly look at means a printer interfacing problem, means how some of the IO transfer methods we discussed earlier can be used there. Well, if you think of the older printers which are available maybe 5-10 years back, they had either serial or a parallel interface. It was called LPT. This parallel interface was almost universally used for printer interfacing. Now, in the parallel interface there are 8 parallel data lines, but nowadays in the computers you will not see the serial ports and parallel ports anymore, they have become obsolete. But in the old computers you may still find some serial ports RS-232C or the parallel these LPT ports available. Okay. Now, the printers that are available today, their number one thing, almost you will see that almost all printers today support an interface called universal serial bus or USB. Now, not only printers, USB has become really universal. Well, almost all the devices today, they have USB interfaces, including our mobile phones. Any device you see, the cameras, everything, mouse, keyboard, everything. So, this LPT port, this used to have a 25 pin connector. Well, all the 25 pins were not used, of course. There were 8 data lines, there were power supply lines, a positive supply, negative supply and a ground, and there were 3 interesting signal lines, a strobe, a busy and an acknowledgement, just using which you could carry out asynchronous data transfer with handshaking. Well, how it was done? Well, the printer is an output device. So, the CPU will be writing some data to the printer, right, the data to be printed. So, after sending the data over the parallel port over these 8 data lines, so it could send 1 byte at a time. CPU will activate the strobe input also, indicating to the printer that, well, I have sent 1 byte of data, you please read it. So, printer can read that 8 bit of data, and during the reading the printer will activate the busy signal. Busy is a signal that is going back to the CPU. Now, after the printer is done and it is ready to accept the next data, the printer will be sending back the ACK signal. Okay. Just using this signal, you can see here you can have handshaking, you can have asynchronous data transfer. So, there are some additional signals like busy, which are specifically printer specific, which of course, in a normal handshaking you need only this acknowledgement is enough, but this strobe and busy are required because this allows two-way handshaking, because CPU knows that the printer is ready, printer will also know that the CPU has sent a data, okay, both ways. So, the printer port actually looks like this, you see 25 pin, you see pin number 1 is the strobe, then there are 8 lines, then there is an acknowledgement, there is a busy, and there are some other pins which are very printer specific, like there is one pin indicates paper out. If the printer is out of paper, this pin will be active. Then auto feed, if auto feed is active, this pin is active. If there is some error in the printer, this pin is active, and there is some ground. Okay. So, this was a interface which was quite popular in the early days, but as I said, today if you look at the printers, they have either USB ports or the more sophisticated ones, they have Wi-Fi connection. They can connect to the wireless, and from a computer system you can print wirelessly. So, what actually I have tried to show through these two examples is that, well, any kind of devices you see, they will have some built-in features, or you will have to find out a way to do it to carry out some kind of handshaking and asynchronous kind of transfers. Now, you see the computer keyboards. Now, you may wonder where is the matrix, who does the scanning and other things. Well, if you break open the keyboard someday, you will see inside there is some circuits. There is a processor or the CPU sitting inside your keyboard only, and it is that processor which is doing this keyboard scanning. It is not the CPU of your computer who is doing this. The processor sitting inside the keyboard is doing the scanning, and whenever a new key is pressed, it will be sending an interrupt signal to our main processor. The main processor will know that, well, a new key has been pressed. Okay. So, you see, newer technologies and newer standards are evolving. Well, one of the main objective is to make the interconnection simpler. Earlier the parallel ports carried 25 wires, but now the USB connections, if you see that there are only few connections, few wires, not many. We will be looking into the details of the USB interface later in the next lecture. But here our objective was to look at a couple of examples, but if you take any other device, any other example, you will see that some similar features or facilities are there. Okay. So, with this we come to the end of this lecture. In the next lecture, we shall be working out some examples, following which we shall be looking into some standard bus interfaces like USB. Thank you.